Here are two pieces of incredibly good news. God's love for us is greater than we'll ever possibly know or imagine. And if we ask Him to, He'll take away our sins so far from us that they can never be found. They don't even exist anymore. That's really good news. This lesson is the second part of section 7.5 in the example spreadsheets notes folder. It is this document, section 7.5 part 2, and it's going to follow section 7.5 part 1 so closely that if you haven't looked at this one, the new one won't make much sense, so I would do that first. It's going to continue looking at this data set, section 7.5 bears, where there were various body measurements taken, and we were trying to predict the weight of the bear based on some other measurements. The note packet looked like this. And one of the things that we did in the first part of section 7.5 was to use all of the other variables as independent variables to predict weight. We did that and got a model that had a very high adjusted R squared. And here is the model. And we might think, okay, we're basically done. But there's an issue, several issues actually. One is, notice this number right here. It's negative 4.23. So what does that number mean? It's a slope. It tells you how much the weight is going to change when the head length changes. So specifically, if head length increases by 1 inch, then because the negative 4.23 is multiplied by an extra 1, the weight decreases by 4.23 pounds. And the question says, does this make sense? No, it does not make sense. Why not? Well, bears who are bigger, that is, who have longer head lengths, should weigh more. And this is saying a bigger bear, a longer head length bear, weighs less. That doesn't make physical sense. There's another issue going on. In our model that we had for all of the variables, the coefficient head width had a p-value of 8.60. It's right here. So that's a big p-value, much bigger than 0.05, and it's telling us that head width is not really significant here. But does that really mean that head width is not a good predictor? What about if we just run head width as the only predictor of weight? Then when I do that, I get the p-value of 1.1 times 10 to the negative 27. And so used as the only predictor, head length has a p-value of 1.1 times 10 to the negative 27, meaning it's a very significant predictor. And so I'm starting to get suspicious. Which is it? When I run my regression with all of the variables, it looks like head width isn't doing anything at all. This is head width. But when I just use head width by itself, then it turns out to be very significant. There's something weird going on here, and let me show what it is. If we go to the spreadsheet, and I'm going to run a new command that we won't really need to use much, but I'm going to show it this time. If I go to the data analysis package and choose a command called correlation, it will bring up this dialog box. And what I'm going to give it are all of the independent variables, all 5 of them. So I'm just highlighting all of columns B through F, and I'll check labels and click OK. And I get a screen that looks like this, which I've copied here in the notes. So let's look at what's going on here. First of all, because correlation is two-directional, A correlated with B is the same thing as B correlated with A, the table is only half filled out. So the correlation between, for example, head width and head length is 0.74, and so I don't have to tell the correlation between head length and head width. So the upper right part of the table is blank. And you see some ones, but that makes sense, right? What's the correlation between head length and head length? Well, it's the same thing. They're 100% correlated, so all of these numbers are 1. But the new and interesting information in the table is down here in the lower triangle-shaped region. And notice that the numbers are pretty large. So for example, neck girth and head length are correlated with an R value of 0.862. And all of these R values are bigger than 0.7, it looks like. So I'm going to draw a so-called Venn diagram picture. Remember, it's just an abstract picture to show how sets are related. And here, if I just think about head length as a variable, it gives some information, which I'm just conceptually drawing as a circle here. And then head width also gives some information about the bear's weight, but head width and head length are correlated, and so I can draw those as overlapping. And here's head width. But then neck girth is also correlated with both head width and head length, and so I can draw it like this, neck girth, and I won't put the others on, but the picture could continue like this. And now if you think about total area kind of as a picture of predictive power, each time we add another variable, we're not really getting our money's worth because a lot of the information has already been captured in another variable. So we could say something like the predictors are giving lots of similar information. And you don't need to hear information multiple times. We already know it once one of the predictors has given us that piece of information. So in particular, in the context of bears, if I already know the chest girth of a bear, I have a very good idea of what its neck girth is going to be. So those two variables together are not adding a lot of extra information. And so that answers what's going on back here. How can head width be significant in one situation and not in another? When head width is combined with all of these other predictors, it's not adding enough new information to be significant, but by itself it is. And you may say, well, big deal, I just won't put it in, but it's this multi-collinearity, this issue is called. This multi-collinearity gives weird information then. It's what's causing this coefficient, and for that matter, this coefficient to be negative when they really shouldn't. And this is kind of misleading information. If I looked at this and didn't know what was going on, I would say, oh, if I want to put a bear on a diet and make it weigh less, then I should stretch out its head somehow. Well, that's nonsense. It's the multi-collinearity that is causing these coefficients to not make sense. And so I should probably remove those variables, or at least remove some variables. So let's talk about now, how do you choose which variables to put in the model? I have this spreadsheet and 5 possible predictors, how do I decide what to end up with? So one way is intuition or prior experience or some theory. If I have an expert on bears, I'll go talk to that person and say, what should I put in? And if I trust them, then maybe that's what I'll go with. But if I'm on my own and just want to kind of follow the data, then there are 2 basic ways to go. One is called forward selection, where I go in stages, and each time I keep adding the next most significant variable. So I've actually done a lot of work. This took me many minutes or maybe an hour or so, but I'll just show the results here in the spreadsheet rather than walking through it on Excel each time. What I did was I always used weight as the dependent variable, and then there are 5 independent variables, and so I ran regression 5 different times and gave the result each time here. So now I'm saying, well, which variable is most significant? I'll put that one in. Well, significance is measured by p-value, and the smaller the better for a p-value. So here's 4 times 10 to the negative 38, 1.1 times 10 to the negative 27, 2.2 times 10 to the negative 69, 3.5 times 10 to the negative 46, and 1 times 10 to the negative 84. All right, these are all very small p-values, but this one is the smallest. And so we'll say that this is the most significant variable, most significant predictor. P is smallest. And so let's put that one into the model. So the variable that went with that p-value was chest girth, and I say now, all right, whatever else happens, my model is going to include chest girth. So then I say, well, should I add another variable? And so similarly, I go through and I'll always keep chest girth included, but now I'll take each of the other predictors, there are 4 other ones, and I'll do regression on each of those paired with chest girth. And so now I'm going to keep chest girth, but I'm interested in knowing which of the other 4, if any, I should put in. So head length has a very large p-value. That's not good. Head width, medium-sized p-value. Neck girth, a very small p-value. Length, medium-sized p-value. It's this one. So this is the most significant additional variable. And so now, whatever else happens, I'm going to include chest girth. I already decided that, and neck girth. And then I'm trying to decide, well, should I put something else in? So now, always keeping neck girth and chest girth, try adding each of the other 3 independent variables. So head length by itself, the p-value is big. Head length with neck girth and chest girth, I should say, the p-value is big. Likewise, including head width, that still gives a big p-value, and length still gives a big p-value. So none of these p-values are less than 0.05. None of these predictors are significant. So no new variable is significant, at least in combination with the other 2 variables that I already have. And so it's time to stop. We won't add anything on this stage. We'll stick with what we had before, and that was to use these 2 variables, neck girth and chest girth. That's one way of doing this. It's actually rather tedious. Again, I took a long time doing this on Excel. Different statistical packages have this built in as an automatic command, and you can get add-ins for Excel to do various things. But using the regular Excel package, the only way to do this is to just manually keep over and over and over again doing regressions. So here's a way that's easier, for at least for doing it with Excel. And that is to start with everything, all the variables, and then keep removing the least significant one. Instead of adding the most significant, we'll take away the least significant. So here is the prediction run with all 5 predictors trying to predict weight together. And I look for the least significant predictor, that is the biggest p-value, and it's right here. This is the least significant. And so I say, whatever else happens, I'm going to throw that one out. Head width is not going to be in my model. Now I have 4 possible predictors left, and so I try them. I run regression with these 4 predictors, and the biggest one is here. And so whatever else is happening, length is not going to make it into the model. Now there are 3 left. I try regression with 3 predictors. This one is least significant, so out goes head length. And then I have 2 predictors left, neck girth and chest girth, and I try those. I've done this before actually, and they are both significant. The p-values are both less than 0.05. So stop removing predictors and use these. You notice in this case, I actually ended up in the same place when I did the backward elimination method as I did when I used the forward selection method. That doesn't always happen. You don't necessarily end up with the same model when you add as when you subtract. But these are techniques to do, and modeling is partly an art rather than a science anyway. So it's okay to have several different tools in your toolbox. And in practice, for us at least, we'll probably use backward elimination just because it's easier to do on Excel. And we'll stop there. Thanks.